Hello, can you hear me? Can you hear me?
Yes,
Okay, thank you. Okay, so welcome back. Today we will study chapter 9, RQ highlights. And I have to tell you that you will see many questions in the final exams related to this chapter. Okay, so be careful. Okay, anyway, um, I will try to finish the 13 chapters as soon as we can, and then I will give you lots of examples to review for the final exams. Okay. Our Q highlight. Okay, so when we replace one hydrogen atom in alkanes by a halogen, we have alkyl halide. So we have alkyl fluoride, alkyl chloride, and then bromide and iodide. Okay. For the nomenclature, the names of alkyl halides, common names which are called alkyl and then halide. For example, methyl chloride or ethyl fluoride. Okay, and for IUPAC names, we call halogenol and then alkane. For example, chloromethane, fluoroethane. Okay, easy. Anyway, so how to make alkyl halide? Okay, how to add uh, one halogen atom to a carbon structure? Okay, the first method, the first method, the first method is uh, to replace OH in alcohol by a halogen atom. Okay, so we need to carry out a substitution reaction. Okay, but we cannot use a salt like sodium bromide or potassium bromide. Okay, uh, because the hydroxide anion, I mean the leaving group. Okay, OH negative OH anion is much more basic than bromide. Okay, we cannot go from a weaker base to a stronger base. We always have to go from a stronger base to weaker base. Always from stronger to weaker and never from weaker to stronger. Okay, so this reaction will not occur. Okay, instead of using sodium bromide or potassium bromide, we need to use an acid, HBr, okay, because in this case, the leaving group is water, and of course, water is less basic than bromide, okay, so we can move from stronger base to a weaker base, okay. In this reaction, after we remove the OH, we have a cation. Okay, so we might have rearrangement. So everyone take a note here. Of course, in this case, we don't have rearrangement for methanol, but for more complicated carbon structure, we might have rearrangement. So take note, take note. Everyone, take note, take note. We might have rearrangement for more complicated structure. I say again, we might have rearrangement for more complicated structure. Okay, so for more complicated alcohol, we might have rearrangement. Okay, and you will see this again in your exam, definitely. Okay. Next. Uh, we can make alkyl halides from alkene CC double bonds. Okay, so by carrying out the addition, electrophilic addition reaction of HBr or HCl, just a normal Markov-Yakov addition reaction. Okay, And again, take note, everyone, take note. We might have rearrangement. Okay, take note. We might have rearrangement because we produce a carbocation, an intermediate carbocation. So whenever you see a carbocation, we might have rearrangement. Be careful. We might have rearrangement. Okay. We can carry out the direct halogenation reaction, but do not use the chlorination reaction because the chlorination reactions might give you a mixture of many products. We don't like that. Okay, the bromination reaction is more selective, and we might have a major product. Okay. Okay, so you already took a note in chapter 4 actually, but anyway, take note again, take note again, take note again, take note again. Do not carry out the chlorination reaction in exams. I say again, do not carry out the chlorination reaction in exams. I mean, in your exam, do not use the chlorination reaction because you have a lot of products. We don't like that. Okay. Okay, so we have alkyl halides. Okay, actually, we rarely see alkyl fluoride or alkyl iodides. Normally, you see alkyl chlorides and alkyl bromides. Okay. So what can we do with alkyl halides? Okay. First, I want you to take some notes. Okay, so look at the first row in slide 8. Okay, so we have C6H5, CH2, Cl, that is phenyl chloride. Okay, phenyl, these phenyl groups. Okay, and CH2 double bond CH2 Br, allyl bromide. Okay, and look at the second row. We have C6H5 Br, phenyl bromide, or you can say bromobenzene. Okay, and CH double bond CHCl, vinyl chloride. Okay, be careful. Vinyl, not vinine. Okay, vinine is not English. It's from French. Okay, vinyl chloride. Okay, so what is the difference between the first row and the second row? Only one carbon. Okay, but the reactivity is completely different. Okay, the benzyl chloride or allyl bromide are very reactive towards the substitution reaction. Okay, and the phenyl bromide, phenyl chloride, or vinyl chloride, vinyl bromides are very unreactive. Okay, completely different. Okay, so take a note, take a note, take a note, take a note, take a note. Everyone, take a note. Do not carry out the substitution reaction. Substitution reaction. Phenyl halide and vinyl halides. I mean the second row. Okay. I say again, do not carry out the substitution reaction of phenyl halides or vinyl halides. Okay, so in your exam, do not carry out the nucleophilic substitution reaction of bromobenzene, chlorobenzene, or vinyl chloride or vinyl bromide. Do not do that. Okay. So what is the typical reaction? What is the typical reaction of alkyl halide? The typical reaction of alkyl halide is the nucleophilic substitution reactions. Okay. As I explained the meaning of the reaction to you in chapter 3. Okay. Nucleophilic. Philic means love or like. Okay. Nucleophilic means love positive. Okay. Nucleo comes from nucleus, nuclei. It means positive. So nucleophilic means love positive. And in order to be able to attack, to love positive, the attacker must be negative. So the nucleophile is something negative or a little bit negative. Okay. So negative attack to positive. So we have nucleophilic. Okay. And this negative attacker will replace the halogen. So we have substitution reaction. Okay. Substitution reaction. There are two cases, there are two options. Option number 1 is SN2 and option number 2 is SN1. So what is SN2 and what is SN1? Okay. SN2 is the abbreviation of the bimolecular nucleophilic substitution reaction. Bimolecular. Bi means two. Okay. Bi means two. So bimolecular means in the rate determining step, there are two species, two molecules. Okay. So look at this example. Okay. We have R2 bromooctane. Okay. The Br, the bromo group is electron withdrawing. Okay, so this carbon becomes a little bit positive, partially positive. Okay, and the hydroxide anion is negative. So negative love positive. Okay, it will attack to the positive carbon. So we have nucleophilic means love positive. Okay, and the OH will replace the Br. So we have substitution. Okay, the thing is, in SN2 reaction, okay, the OH negative, the OH anion will attack to this positive carbon before the bromine atom say goodbye to the molecule. The bromine atom is still here. Okay, the bromine is a little bit negative. OH is negative. So negative, there's a line negative. Okay, and the bromine atom is still here. It occupies this space. Okay, so because of steric effect, the OH anion will attack to the opposite side. If the Br is on the left, the OH will attack to the right. And if the Br is on the right, the OH will attack to the left. Okay, so what happens? Eventually, we have the inversion of the configuration of this asymmetric carbon. If the starting material is R, the product is S. And if the starting material is S, the product will be R. Okay. So this is SN2. So for SN2, we have one product. And if we have asymmetric carbon, okay, we have one product with opposite configuration. That is SN2. The second case is SN1. SN1 is the abbreviation of unimolecular nucleophilic substitution reaction. Okay, unimolecular nucleophilic substitution reaction. Uni means one. Okay, unimolecular, that means one molecule. Okay, so what happens? So in an SN2 reaction, for example, look at the tertiary alkyl bromide. Okay, first, the CBr bond breaks. And we have a cation. Okay, so the Br, the bromine atom, say goodbye to this molecule, and then we have the cation. Okay, and this step is the rate determining step, the slow step. Okay, so in this step, we have only one molecule, this alkyl bromide. So people give it a name unimolecular. Okay, that means one molecular. Okay, so we have a cation and of course the bromide anion. Okay, so look at the cation. You know, this cation has a trigonal planar structure. I mean, it is flat. Okay, so we don't have the bromine here. So the negative oxygen will attack. It can attack to the left. It can also attack to the right. It can attack from both sides. Okay, so what happens? So eventually we will have two products, approximately about 50% S and 50% R. Okay, so we have two products, half S and half R. Okay, so everyone take note, take note, take note, take note. Take note, everyone. Note number one. S and one reactions. We have two products, about 50% S and 50% R. I say again, in S and one reactions, we have two products, about 50% S and 50% R. Okay. Note number two. Note number two. In SN2 reactions, we have only one product with opposite configuration. I say again, in SN2 reactions, we have one product. We have only one product with opposite configuration. Okay. So I say again, SN1, two products. SN2, one product. Okay. In your exam, we will not tell you which reaction is SN1, which reaction is SN2. We don't say anything. Okay. You have to make a decision. Which reaction is SN1, which reaction is SN2. SN1, okay, two products. SN2, okay, one product. Okay. So the most difficult thing is, how do we know which reaction is SN1 and which reaction is SN2? How do we know? How do we know? Actually, it is not easy. Okay. It's not easy. Anyway, I will help you. That's why you need me. Okay. Okay, so in this reaction, in the reaction mixture, what do we have? We have the alkyl halide. That is number one. Number two, we have the nucleophile, I mean the negative attacker. Number three, we have the solvent. Okay, so we need to look at these three things. Okay, number one, we need to look at the alkyl halide. Alkyl halide. Alkyl halide. Okay, so for the alkyl halide, we have primary, secondary, and tertiary. Okay, tertiary. If the reaction is SN1, first the halogen atom will say goodbye to the molecule, and then we have a carbocation. Okay. So if you want to produce a cation, that cation must be stable. Okay. So I asked some of you Lư Minh Anh, are you there? Minh Anh, Lư Minh Anh. Turn on your microphone, Minh Anh. Are you there? Minh Anh, turn on your microphone. You don't have a microphone. Turn on your microphone. You don't have microphone. You don't want to talk to me. You hate me. Nguyễn Bá Giang.
Yes, teacher.
Okay. So can you tell your friend which cation is more stable? Tertiary cation or primary cation? Which one is more stable?
I think it's tertiary.
Okay, tertiary cation is more stable. Why is that?
Because in the tertiary there have three CH3, which one is giving
Giving what? Donate what?
donate electron.
Okay, electron by hyperconjugation. Okay, so tertiary is more stable. So tertiary will give you SN1 or SN2, Yang?
I think is SN1.
Okay, good, very good. Thank you. Okay, so for tertiary alkyl halide, because the cation is stable, so we can have the cation. That means we can have SN1. Okay, primary alkyl halide cannot give you SN1 because the primary cation is not stable. It cannot be formed. Okay, so everyone take note. Everyone take note. Note number 1. Tertiary alkyl halides will give SN1. I say again, tertiary alkyl halides will give SN1. Second note, primary alkyl halides will give SN2. I say again, primary alkyl halides will give SN2. Okay, so tertiary SN1 means 2 products. Primary alkyl halides SN2 means 1 product with opposite configuration. What happens with secondary? We don't know. Okay, so by looking at the structure of the alkyl halide, if it is tertiary, we know it is SN1. If it is primary, we know it is SN2. But if secondary, we don't know. Okay, so what can we do? We don't know. So for secondary, we don't know yet. So we need to look at the next reagent. Okay, that is the nucleophile, the negative attacker. Okay, you know, in the SN1 reaction, the rate determining step, I mean the slow step, there is only one molecule, that is alkyl halide. So the concentration or the structure of the negative attacker, I mean the nucleophile, will not affect the rate of the SN1 reaction. Okay, it doesn't matter. But for SN2, in SN2 reactions, in the rate determining steps, we have 2 species, the alkyl halide and the nucleophile, I mean the negative attacker. So the concentration and the structure of the nucleophile will control the SN2 reactions. Okay. For primary, we know it is primary alkyl halide, we know it is SN2. For tertiary, we know it is SN1. For secondary, we look at the nucleophile. So if the nucleophile is strong and high concentration, Is it easier or more difficult for SN2 reaction? Lê Hoàng Long, are you there? Lê Hoàng Long, Lê Hoàng Long, Lê Hoàng Long, are you there? Lê Hoàng Long, absent, you log on and sleeping. Nguyễn Cao Bảo Long, Bảo Long, Bảo Long, are you there? Nguyễn Cao Bảo Long, Nguyễn Cao Bảo Long, are you there? Nguyễn Cao Bảo Long.
Yes.
Okay. Can you tell your friends if the nucleophile, I mean the negative attacker, it is strong and high concentration? Is it easier or more difficult for the SN2 reaction? Easier or more difficult? High concentration and strong.
I think it's easier.
Okay, easier. Okay, good. Okay, thank you. So everyone, take note, take note, take note, take note, everyone, take note, take note, take note. For secondary alkyl halides, I say again, for secondary alkyl halides, we need to look at the nucleophile. The nucleophile, I mean the negative attacker. We need to look at the nucleophile. Okay, continue. If the nucleophile is strong with high concentration, I say again, if the nucleophile is strong with high concentration, sorry, we have SN2. SN2. Okay, continue. If the nucleophile is weak with low concentration, we have SN1. I say again, if the nucleophile is weak with low concentration, we have SN1. Okay. Okay, so strong and high concentration, SN2. Weak and low concentration, SN1. But unfortunately, life is not that easy. Sometimes we have strong but low concentration. Sometimes weak but very high concentration. Okay, complicated. So we don't know. Okay, so in that case, we cannot make a decision. Okay, so we need to look at something else. We need to look at the solvent. We need to look at the solvent. Okay, we need to look at the solvent. Okay, for the nucleophilic substitution reaction, we need to use a polar solvent. Polar solvent, because you know the nucleophile is polar, so we need to dissolve the nucleophile. For example, sodium hydroxide, we need to dissolve in a polar solvent. Okay, so we have to use polar solvent for these reactions. But there are two kinds of solvents here. First, aprotic solvent and protic solvent. Protic solvent means we have a proton, and aprotic or non-protic solvents means we don't have proton. Okay. Okay. So for protic solvent, for protic solvent, for example, water is protic. Okay, we have proton. Or methanol or ethanol, we have proton. Okay. So if you want the reaction proceed with SN1 mechanism, you need to produce a cation and the anion. Okay, the C-Br bond will break, and we have a cation and the Br negative anion. Okay, looking at the cation, we don't know yet. We don't know. We cannot make a decision. So look at the anion. Okay, so in polar protic solvent, we have a proton. Proton is positive and positive will neutralize the negative anion, neutralize the negative charge on the anion. So eventually, the negative charge of the anion will be decreased. And then the anion is stable. The anion is stable means we can break the CBr bond to produce a cation anion. That means we have SN1. For aprotic solvent like DMF or DMSO, DMF is dimethyl formamide and DMSO is dimethyl sulfoxide, I mean CH3SO CH3, or acetone, you know acetone, CH3CO CH3. In this solvent, we cannot have proton. Okay, so for non-brotic solvent, we don't have proton, so we cannot neutralize the negative charge of the anion. So we cannot produce anion. That means we cannot produce the cation. That means we cannot go with the SN1 reaction. Okay. So everyone take note, take note, take note, take note, take note. Note number 1. For protic solvents like water, methanol, ethanol, we have SN1 reactions. I say again, for protic solvents like water, methanol, ethanol, we have SN1 reactions. Okay. That note number 2. Note number 2. For aprotic solvent or non-brotic solvents, for non-brotic solvents like DMF, DMSO, or acetone, we have SN2. I say again, brotic solvent like water, methanol, ethanol, SN1. Non-brotic solvent, aprotic solvent like DMF, DMSO, acetone, we have SN2. SN1 means 2 products, and SN1 means 1 product with opposite configuration. Okay, so by looking at these factors, we know which reaction is SN1, which reaction is SN2. Okay, and you can give the correct products in your exam. Okay. Just ignore some slides. Okay. So we have many examples of the nucleophilic substitution reaction. You know, it's not just the hydroxide anion. Whatever negative can attack to the positive carbon. That means the carbon connected to the halogen. And we have substitution reaction. We have many examples. Okay. But with one condition. Remember, we always move from stronger base to weaker base. We never go from weaker to stronger. Remember that. Okay, always from stronger to weaker and never from weaker to stronger. Okay. We have one example, that is Williamson ether synthesis. Okay. You know, ether at high school, you know, diethyl ether, I mean C2H5O, C2H5. At high school, you know that ether, you study that ether. I have a question. Nguyễn Hữu Sinh, are you there? Nguyễn Hữu Sinh. Okay.
Yes.
How do we make? Can you tell your friend how we make diethyl ether? I mean C2H5O, C2H5. From what?
I think we use ethanol.
Good. And with the catalyst, what is the catalyst? Acid or base?
Acid.
Okay, very good. Okay, thank you, Sin. Okay, so if you want to make diethyl ether, we just use ethanol and acid catalyst. Okay, but if you want to make, look at this one, butyl propyl ether. I mean, 3 carbons, oxygen, and 4 carbons. Okay, if you mix butanol with propanol, so we have 3 products: C3C3, C4C4, C3C4. We don't like that. We just want one product. Okay, and Professor Williamson invented this method. Okay, first we remove the proton from alcohol by using sodium hydride. I mean, use a strong base to remove the proton, and then we have anion. And we carry out the nucleophilic substitution reaction with a second alkyl halide. For example, here we have propyl bromide. Okay. So look at the CH2Br. This carbon is a little bit positive, partially positive, because the bromine atom is electron withdrawing. Okay. Oxygen here is negative. So negative attack to the positive carbon. So we have nucleophilic attack. Okay. And this negative attacker will replace the Br, so we have substitution reaction. Actually, it is SN2 reaction, and then we have the ether. So we can make C3O, C3, C4. Of course, we can make C3O, C3. Okay, so this method is more general than the method from alcohol. Okay. The thing is, this is a strong base. Okay, strong base. So you might have elimination reaction. Okay, so everyone take note, take note, take note, take note, take note, take note. Do not carry out the reaction of tertiary and secondary alkyl halides. I say again, do not carry out the Williamson ether synthesis of tertiary or secondary, because we might have elimination reaction. We have many products from the elimination reaction. Okay, so this reaction, I mean the ether Williamson ether synthesis is useful for primary alkyl halides, not secondary, not tertiary. Okay. Okay, so that is a substitution reaction. Second typical reaction of alkyl halides is elimination reaction. Elimination reaction. Okay. Elimination reaction. Okay, so in an elimination reaction, groups of atoms are eliminated from a reactant, and then we have a double bond. Okay. For example, we remove HBr or HCl from alkyl halide, and then we have double bond. And the main product is the double bond that has more hydrogen that can donate electron by hyperconjugation. I mean, double bond get more hyperconjugation. And if we have conjugation, so the main product is a double bond with conjugation. You know, conjugation is stronger than hyperconjugation. Okay. Okay. So take the conjugated system because it is more stable. But normally you don't have the double bond. Then take the double bond with more hyperconjugation. Okay. For example, from 2-bromobutane, the main product is 2-butene, not 1-butene, because the double bond in 2-butene has more hyperconjugation hydrogens. Okay. However, if the base is big, and how big is big? I already told you. From T-butyl is big. Okay. From T-butyl is big. So if you touch butoxide, this is a big base. Okay. If the base is big, okay, the reaction will go with the less steric way. Less steric way. Okay. You know, in this case, from 2-bromo to methylbutane, because the base is big, so it's difficult to take this proton from the CH2. Okay. So it will take proton from CH3. So the main product is 2-methyl-1-butene. Although this double bond has less hyperconjugation hydrogens. Okay. Okay. So remember this one. I already asked you to take a note. Okay. From T-butyl is big, and when the base is big, because of the steric effect, the reaction must go with the less steric way. Okay. And if we have asymmetric carbon, if we have asymmetric carbon, so remember, this is anti-elimination. I mean, the hydrogen and the Br or Cl, I mean the chlorine or brominatom, must be anti to each other. I mean the H and the halogen must be on the same line with opposite direction. Okay, if the hydrogen is close to you, the halogen must be far from you. If the hydrogen is far from you, the bromine must be close to you. Okay, so everyone take a note here on slide 33. Take a note on slide 33. You will see this one again in your final exam definitely. So take a note here. Take a note here. Take a note here again. In E2 reactions, we have anti-elimination. I say again, in E2 reactions, we have anti-eliminations. That means the hydrogen and the halogen must be on opposite side. Opposite side. Okay, that means the hydrogen close, the halogen must be far. If the hydrogen is far, the halogen must be close. Okay, take this note. I will give you some examples to do today, but this is important. You will see this again in your exam definitely. Okay. Okay, and take one more note. Take one more note. One more note here. In SN1 reaction and in E1 reaction, actually you rarely see E1. Okay, so in your exam you just see SN1, SN2, and E2. Okay, take note. In SN1 reaction, be careful, we might have rearrangement. I say again, in SN1 reactions, we might be careful, we might have rearrangement. Okay, let me ask someone. Lý Quang Vinh, Lý Quang Vinh, Lý Quang Vinh, Lý Quang Vinh. Are you there, Vinh? Lý Quang Vinh, Lý Quang Vinh. Absent. Nguyễn Thị Cẩm Tú, Nguyễn Thị Cẩm Tú.
Yes.
Okay. Cẩm Tú, can you explain to your friends why we have the rearrangement here?
Because the carbon in
tertiary. You mean
tertiary is more stable than the secondary.
Okay, why is that? Why the tertiary cation is more stable? Because
it's have more the donating
hydrogen. Okay, how many hyperconjugation hydrogen here in the tertiary? How many hyperconjugation hydrogens? How many? Two?
3.
Only 3? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many? Count it. In tertiary, in the tertiary cation, how many hyperconjugation hydrogens? Just count the hydrogen that can donate electron by hyperconjugation.
4.
Only 4. Count it. The hydrogen on the carbon next to the positive carbon. How many?
5.
How many? Just count it. How many? On the carbon next to the positive carbon. How many hydrogen do we have?
It's 5.
Only. How come it's 5?
I don't know.
Count it. Do you understand? Count the hydrogens on the carbon next to the positive carbon. How many hydrogens atoms do we have?
It's 6.
Count it again. Look at the carbon right next to the positive carbon. You understand the meaning of right next to?
Yeah.
Okay, then count it. How many hydrogens do we have?
7.
Okay, good. 7. Okay, so on tertiary carbon we have 7. How about on a secondary cation? How many hyperconjugation hydrogens? How many? 2? For the secondary, how many?
6.
How many?
6.
How come it's 6? Do you understand the meaning of right next to? Look at the carbon right next to the positive carbon. How many? How many? 2. Adjacent to, right next to. Count it. How many? 2?
I don't know.
How come you don't know? Count it again. You should know. Look at the secondary cation. Okay. Look at the positive carbon. Okay. And then look at the carbon next to that positive carbon.
3.
Okay, 3. Good. Okay, just 3. So for secondary we have 3 hydrogens, and for tertiary we have 7 hydrogens. Okay, good. Okay, thank you, Tu. Okay, so we have rearrangement. So everyone, be careful. We might have rearrangement. I said rearrange a million times, but half of you will forget, will not remember, and half of you will lose 4 marks in your exam. So be careful. All right. All right. Now take a break for 10 minutes. I think 10 minutes. Okay, and after the break, we study a very important section, that is the Grignard reactions. In this section, we will have 5 reactions, and you need to learn by heart all of them, because you will see all of them again and again and again in your exams and your final exams. Okay, so everyone take a break for 10 minutes. Okay.